Alrighty, good morning, guys. Can you hear me?
Yes, I can hear you.
How are we doing?
Pretty tired, but all right, I guess.
Yeah, it's gonna be nice getting a few days off here, right? So we're just gonna have the lecture this week, and then there'll be no more for the rest of the week. And then on Tuesday we'll have the next lecture, and then so on.
Okay.
Are there any questions or comments before we get started? My plan was to, so last time we did a bunch of fixed income theory. My plan was to do some examples in the beginning and then try to do a little bit more fixed income in the second part of today's lecture. So let me just recall some of the things we talked about last time. So we're doing fixed income. Right, so the starting point is the interest rate. So those are the interest rates. Then you use these to create the money market account. So the money market account has prices. So this is SN plus 1. This is equal to the previous one, SN, times the interest rate. And it starts out at, we just normalize it, it starts out at 1. And so the thing to note here is the indices. This one here, this is N and not N plus 1, right? So what it means is that, so at time N, you know what Sn plus 1 is. So you can foretell what the interest rate is over the next period. You know what this is, but you don't know what Sn plus 2 is. So you can look, you can foretell, you can predict the interest rate in the money market account over one period, but not over two. Okay, so that's the starting point. This is what you're given, and then you form zero coupon bond prices. So these are denoted by B, N, M. So here N runs from 0 to M. M is some natural number. So what these guys do is we have a timeline, and M is the maturity for the zero coupon bond. So a zero coupon bond is a bond that pays out only one time, and it pays out $1 at time M. And so N here runs up to M, and what we're interested in, so this is 0, just here's N. What we're interested in is figuring out what should the price be over here at an earlier time. So this number here is going to get moved over to time N, and we're going to denote that by Bn M. So this is typically going to be smaller than 1, or something positive, but smaller than 1. And the way that we set this up is we're going to have two requirements. So one of them is going to be that if I look at the zero coupon bond, when I move n up to m, I'll have that the zero coupon bond price is equal to 1. And the other one that I want is, so this here is my terminal condition. And the other one that I want is B and M should be arbitrage free. So I need to have the property that when I divide by the money market account, so this here runs from 1, 0, 1 all the way up to M. This is a martingale. So this here is the no arbitrage condition. So if you combine these two, we are led to, what are we led to? We're led to saying that if this is a martingale, then I'll have that condition here. The condition here on if I need something that's smaller than n, so if k, so I take k to be less than n, I'll get that this is bk m over sk 0. And so what I can do is, if I move n here to be m, I know what the terminal one is. So take n to be m. And what I'll end up with is bk m over sk 0. This is equal to e of b m over s m 0 given k. Right, and now this quantity here is 1. I can move this one over to the other side. I'll get that the zero coupon bonds, they're going to be of the form sk0 over sm0 given if k. And this is true for k running up to m. Another thing that's custom is that when you start out with a measure, you call that measure for p tilde, because that measure is going to become the risk neutral one. But so we can put tildes everywhere here. So when you define b k m to be this formula, for a given measure, p tilde becomes a martingale measure. So this is the starting point for fixed income. We collect, we have a sequence of random variables, and we form the money market account. Given the money market account, we can form the zero coupon bonds. And so now we have a model, right? So we can now trade. So at this point, we can trade So at time K, we can trade the money market account, and we can trade the zero coupon bond, BK, and then M, and then we can trade these for all M, going from K plus 1 to infinity. So just to contrast this, to the equity models, we had before, but there we could trade. There we could trade the money market account, and we could trade the stock. So before we could only trade 2. In these fixed income models, we can trade many more. We can trade all these zero coupon bonds. Are there questions up to this point? We've been talking about this for a few weeks. The thing we spent a lot of time on last time was forwards and futures. So last time we started with forwards and futures. So let's talk a little bit about them, and then let's do some sample problems. So a forward. Let's do that one first. So a forward. Now we're looking at a time period. So let's fix the maturity. This is N. So again, this is time. This quantity here, this is when the forward expires. This is when the forward expires. And this here, if we're sitting at, say, little n, this here is current time. So what happens with the forward is that there's going to be a payoff out here at the end. And the payoff is going to be, so keep in mind, now we're up here, we're not in the red stuff, we're in the top part here. There's going to be a payoff, and the payoff is going to be given by, say, Sn, and then minus a strike, and the strike, this is where the current time comes in, this is Kn. So this here is the payoff of the forward, and the payoff is coming at time n. So this payoff here, this is of course going to be random because it depends upon what S capital N is. So this is a forward on Sn. For some process Sn. And we talked about before, there were 2 cases where it could either be traded or non-traded. And traded, this could, for example, be a stock. And the non-traded one, this could be, for example, be an interest rate. Interest rates are not price processes, right? But the stock has a price process. And so what we do is we have this random payoff. Like for the zero coupon bond, it's a different story. For a zero coupon bond is $1. So this is $1 we move to an earlier time. For the forward, it's a stochastic quantity, and we move this to an earlier time. So we want to move this to an earlier time, and we want the value at this earlier time to be 0. So that's the key thing. Kn is called a forward price, so that's the keyword, forward price, if the time n value of getting this difference, what's it out here, is capital N minus Kn, of getting this thing at time n is 0. So this strike here is the value at time n of getting this quantity at maturity is 0. Okay, so what should that be then? Well, we'll use the discount. So the value at n, we'll discount it. So we'll discount it back. So we have the payoff. Right, there's no plus here. There's no pluses or minuses here. No pluses. There's not a plus. Like for the call and the put, we would have parentheses and then we take positive part. This is not the case. This is not the case for forward. So the value here is, so this is the payoff. So we discount the payoff back. And discount the payoff back by the money market account. So that brings back time 0, and then I move forward to time little n. And then I compute the conditional expectation. So this is going to give me the value of this payoff at that earlier time. And so what I want to do is, I want this to be 0, and this here is needed. This is needed for Kn to be a forward price. Any questions up to this point? So you can see here, we can solve for Kn, right? Because Kn, this is going to be Fn measurable. So the thing that is not Fn measurable here is this ratio. So we can solve this thing here, and we'll get that we can solve this thing here. What will we get is E tilde Sn divided by Sn0 times Sn0 given Fn. What will that be? We move this to the other side. We get Kn and then an expectation of Sn0 or S capital N. And what I have here, this is my zero coupon bond price. So this gives me a formula for Kn. So if I solve, I'll get Kn. So I'll get Kn divided by B and N, and then this conditional expectation on top. There you go. And it's also here, you can see that it's going to start making a difference if SN is traded or not. Because if SN is traded, then when I discount by the, if I discount by the money market account, I'm going to get a martingale here. So if, so this is a big if, but if SN is a price process, we can simplify, and we just get SN divided by the zero coupon bond. But that's a big if. Any questions on this part? Yeah, we good? Then the forwards is it's quite similar, except you get payments throughout. So for futures, so now the futures price, here the futures price process. This is this, we denoted it by phi, phi n goes from 0 to expiry. And so what happens is that instead of just having one payment here at the end, at time n, the payment would be, it would be Sn minus, and so here it will be phi n minus 1. There will be multiple payments throughout. There will be a payment here, there will be a payment over here, and the payment over here is going to be phi n minus 1 minus phi n minus 2, and so on, all the way down to time 0. So there will be payments. So at n equals 1, 2, up to capital N, there's a payment. This could be positive or negative. There'll be this payment phi n minus phi n minus 1. And then if we want to have this formula, we need to say what is phi n here. So with phi n being that S we have over there. So last time we saw, we proved a formula that said that phi n is equal to the conditional expectation of that terminal value. All right, so in particular, futures martingales on the p-tilde, because it's a conditional expectation of a random variable, and this is what we call for a Levy martingale. So the difference between futures and forwards is that you have these warning payments that are coming along. Are there any questions about these two slides or these couple of slides? And then if not, we will look at a couple of old exam questions that were given out in the past. Let's see, the first one I had in mind was number 8. Let me share my screen so you guys can see it. Okay, so the first one here is problem number 8. So you see the starting point is you're given this interest rate model. So using the interest rate model, you can now go follow the first slides that we had where you form the money market account, and you compute the zero coupon bonds, and so on. So this question here is about futures. So there's a future contract, and the futures is written on the rate. So we know that in this case, the rate, there's no martingale property of a rate, right? Because the rate is not a price process. So there's no mark. So we're outside the world where this thing is the value of a traded security. It's just the interest rate. And so what we're being asked to do is to compute these futures prices. And there's a hint to what the futures price process is going to look like. It's going to have this linear structure. So let's start by trying to figure out what these futures prices are like. So this is number 8. So we have a model for the interest rate, Rn plus 1 is defined to be 1 plus Rn times these epsilons, where epsilon n, your IIDs, and the coin flips, you go up to U, you go down to D, the probabilities P tilde and Q tilde, and the IID. And then we're looking at a futures with futures prices. Here it's called F, so let me call it F the same as in the FK. And the terminal condition, that's the important one because this is how we get started. Fn is exactly that R here. This is Rn. Right, so our job is to find Fk from 0 to n minus 1. And so how do we do it? Well, we're in the setting of this last slide here, so we're going to use this formula. We're going to use this formula, so we will start by computing this conditional expectation by going from capital N to capital N minus 1. So we will go from we'll compute the conditional expectation of R Rn given Fn minus 1. Right, this is going to be that's going to be the second last one. This is going to be our Fn minus 1. Right, so let's work out what this here is. So this will be plug in what the formula says it is. This is Rn. This is going to be 1 plus Rn minus 1 epsilon n given Fn minus 1. And this is a situation we've had many, many times before. This thing here, this is Fn minus 1 measurable. This quantity here, this is independent of Fn minus 1, and this is where we're using this IID assumption. Of course, I should have been more specific here, like our Fn, this is the sigma algebra that the epsilons generate. So this is independent. This thing here is measurable. This thing that's measurable can go outside. And we just take on conditional expectation of the remaining components. So this is 1 plus R n minus 1, and then an expectation of epsilon n. And then what we will have here will be 1 plus R n minus 1, and the expectation of these guys, this will be P tilde U plus 1 minus P tilde D. So we see here that the futures price at time n minus 1 is an affine function. Like this one here is, this is affine. This is an affine function of Rn minus 1. And this is, of course, also an affine function of Rn. So this leads us to this conjecture that, so we're going to make the guess. So we're going to make a guess. We're going to say that the futures price at time k, this is an affine function. So this is affine function of Rk for constants Ak and Bk. So at least it works when I have k equal to n. When k is equal to n, I have that my f is just r. Right, so when k is equal to n, then I get that a n is 0, b n is 1. There the guess works. Some people call this for a conjecture. Some people call it for an ansatz. It's just a guess. And then we're going to check that it's true, but at least we can see fairly easily that it's going to be true at the last 2 points. And what is it for the other one? This is 1, so we get this quantity over here. So a n minus 1 is equal to p tilde u plus 1 minus p tilde d. And b of n minus 1, that's the coefficient in front of r, so that's the same coefficient. So now the question is it going to be true in general? So what we need to check is, do we have that if I take, so let's do an induction step. Let's do an induction step. If I take the conditional expectation of a n plus 1 plus b n plus 1, then I'll have my r n plus 1 given if n. I want to prove that when I compute this conditional expectation, I'm going to get something that has exactly the same form, but of course, potentially with different coefficients. Like these coefficients here, they change over time. Right? 0 becomes this coefficient, 1 becomes this coefficient. So let's try to compute this. Well, this is a constant, so he's just going to go outside. And that's another constant, he can go outside the conditional expectation. And then I'll replace in plus 1 with the formula we had. In plus 1 is on the left-hand side, so we will replace it with what's on the right-hand side, 1 plus Rn times these epsilons. And so now we have the situation we had before. This one here, this is Fn measurable. This part here, this is independent of Fn. So we are in this familiar situation. We pull this one outside and just take unconditional expectation of the last part. So we write that out. We take this part outside, 1 plus Rn. And then instead of conditional expectation of the epsilon, we just take the unconditional expectation. And we already had computed what that unconditional expectation was. This was p tilde u plus 1 minus p tilde d. And what I want this to be, this is the question, is this the same thing as an plus bn times rn? And the answer is yeah. I just need to match up coefficients properly. So if I look at the connection between a of n and b of n, what are they going to be equal to? Well, a is going to pick up all the constants, so that will be this one. And then it will be bn times this coefficient over there, p tilde u, 1 minus p tilde d. And b will pick up whatever's in front of r. Okay, so that will be bn plus 1 times this coefficient. So you can see here, B has some sort of a multiplicative structure. And we know that the Bn is going to end up being 1. That's the terminal condition. And these ones here are our terminal conditions. So it's going to end up being 1. Okay, so let's try to work out. So it's a multiplicative structure. It's going to end up being 1. So B of n is going to be p tilde u plus 1 minus p tilde d to power n minus little n. And of course, the a's, those are easier because at this quantity we have here, this is exactly what bn. Right, so I have an is equal to an plus 1 plus bn. This is an additive structure, so we will write out a of n. This is going to be summation from k equals n up to n minus 1 of b Okay. So this gives us the future spice process in in the specific model for the interest rate. The futures price is simply going to be if n, this is going to be this coefficient, the sum a n plus b of n times Rn, where these coefficients have this recursive structure of them. Any questions or comments on this part? You guys are very quiet. That's what we're doing here. Is this something we can follow? Meow has a question. How did AN? Yeah, let's see if we can get AN out again. See if we can get AN out again. It's this formula here. Well, so there were so this here is kind of like this is not really needed. I'm happy if you can get these recursions out there. So how did you get the recursions? So this one here, this is the important part. This is most important. This is most, so the recursions, these are important. Okay, so how did I get the how did I get them? Well, so we did the calculations down to here. And this one here, this is going to be my f n. So the conjecture is that fn is an affine function and it has the coefficients are a and b. And so how do I make sure that this question mark here is correct? Well, what I'll do is I'll match up random coefficients and I'll match up constant coefficients. So what I have here, these are the Rn coefficients. These ones here are the non-random parts. So what I did was I said, let's look at the non-random parts. Okay, so everywhere there is an R, we just forget about it. So you have AN, that's this one. And then you have AN plus 1, that's this one. And then you have BN, forget about the R, so you just have a 1 here. And then it's this coefficient. So then you have BN plus 1, and then that coefficient here. So that's going to give us a connection between AN and AN plus 1 is this term that comes in. So that's the non-random parts. And then the random parts, well, that's the one that has to do with R. So you look for R's everywhere. You take the coefficient for R in this bottom line. This is going to be my BN down here. And then I look for RNs upstairs. So there's no R here. Here there's going to be an R, it's going to be BN plus 1. Okay, so I'll copy that down here, and then I have the remaining part again. So I'll copy that one over here. And these ones here are the recursions. Does that make sense, Mel? Great. Other questions about this part problem?
For a question like this, where they have like a given maturity, will we always expect like fk to be like in terms of like ak plus bk rk?
Yeah, so this particular form here is very nice, right? This is a very nice form. This is affine in R. So this is
Yeah.
very, very simple.
Mhm.
And what makes this form so simple is because the interest rate up here has this very simple form.
Right.
So if you start changing what you have here to something else, like for example, you could put a square here.
Yeah.
Say it should be 1 plus Rn to the power 2 times these epsilons.
Mhm.
Then it becomes a different story, right? Because
Right.
you will not have this anymore.
Oh.
Because, for example, if you put a square here, so we can just let me try to do it on a different sheet. So if I switched it around such that I got Rn plus 1 was now defined to be, say, 1 plus Rn, and I put a square, and I keep everything the same. So now what would happen? Well, I don't know what would happen. We can try to get an idea about it. So again, I would go backwards. So I would start by saying that fn minus 1 is going to be the conditional expectation of fn given fn minus 1. And so you use the requirement that at the end, this is exactly the interest rate.
Okay.
So we get Rn here. And so now we'll use the formula. And you get E tilde 1 plus Rn minus 1, and then you get the square. So that was a new thing compared to before, and this would be epsilon n given fn minus 1. And so what will become now is, this is again going to be measurable. So you pull him outside, and this would be 1 plus Rn minus 1 squared. And then you get this P tilde P tilde
q tilde d.
But you see now this doesn't have the same form as before. This is not equal to a of n minus 1 plus b of n minus 1 times.
Okay.
Right, because there's a square.
Mhm.
But you can almost, what would your guess be how do you need to correct the formula here to make that thing be not different, but actually equal to? How would you correct the bottom formula? Okay, so that's not true.
Yeah.
But if you want to make it true,
n minus 1 squared.
yes,
as well.
Very good. So this would be a C.
Oh, okay. So it's a matter of like transform, like depending on like what Rn plus 1 is, you could transform Fn.
Yes.
Okay. That makes sense.
So now you can see how you make exam questions, right?
Yeah.
Yeah. Okay. So this works for one step back. The question is, does it also work in general?
Okay.
So what you're learning here, Don, is that if I change the dynamics of the interest rate, that's going to have an immediate impact on what the
forward price.
Futures. This is
future price.
Yeah.
Yeah. Okay.
So, Professor, does it mean the linear combination is the best guess in these scenarios?
It's not that it's the best guess. that is the form. Like in the previous one, when you do induction, right, you come up with a guess, right, and then you do the base step. Right, this here is the base. This is the base step. And so we checked that the base step. So here we actually did 2. You don't have to do 2, but we did two base steps here. And then you do the induction step, and that's good enough. So you come up with a guess, and then you check.
Got it.
So this is no longer, after we do the checking, this is no longer a guess, right? That is correct. And so what Dawn was doing was she said, let's play a little bit with the form. Would you still make such a guess if I put a square there? And what Dawn realized was that no, I would not make such a guess here anymore. The guess that I would make would be, I would add a third term here where I put a square on the R. So she would get down to here, and now, if I understand Dawn correctly, she would now make a guess. So this is going to be Dawn's guess. Correct me if I'm wrong, Dawn, but I think one could start with a guess of this form: an plus bn times rn plus cn times rn squared. But of course, up to this point, it's just a guess. The base case is okay.
Yeah. Mm-hmm.
So to make this guess correct, we have to check. We have to check the induction step.
Right. Because we still have to find like AN, BN, and CN.
Yeah. So we can do the induction step, and we did it before. We can try to do it again.
Okay.
So we'll work out what this step here is, and does it have the right structure? If it does, then Dawn is right. Her guess is actually correct. So let's just work it out. I don't think it's such a big deal. We will plug in these values here at a later time. And your R n plus 1 plus C n plus 1 R n plus 1 squared given Fn. So Dawn, I can see trouble coming. I don't think your guess is correct. But let's try it. Here I'll get A n plus 1 plus B n plus 1 times, and then the conditional expectation of R n plus 1. We had that a few times. So this is where we use the formula. So we use the formula with the square now. So this here is 1 plus R n squared. And then we need the expectation of the epsilon. So that was the one we have over here, P tilde U plus 1 minus P tilde D. And here is where I think there's trouble with Dawn's guess. C of n plus 1, and then the conditional expectation of the square. Okay, so we plug in what that is. So now we're going to get 1 plus Rn, but then you have to square it.
So does that be like part 4?
So you see, this is where the trouble is.
Okay.
Because now what is going to happen is this thing here is again measurable. He goes outside, and you have the expectation of this thing squared. Okay, we'll work out what that is. This is A n plus 1. I just copied the first line. And then you'll have your Cn. And now this thing is measurable. He goes outside. And then the expectation of this thing is P tilde, and then you have U squared plus 1 minus P tilde D squared.
Okay.
As before, right? We need to make sure that you have the structure, but now with a C.
Mm-hmm.
So we write this as a question mark. Is this equal to AN Cn Rn plus Cn Rn squared. And you can see now this is trouble because you have Rn to the power 4 here, and there is no power 4 over here.
Right.
So this is not true.
Okay.
So it worked. It worked for the base step, but it doesn't work for the induction step.
Okay.
So this is
This is not right.
this is not right. This is not right. So I forget who asked the question about whether or not it's so making guesses. This is one thing, but we should check that these guesses are correct. And just because you check something for the basis step in an induction argument, this is not sufficient to verify the guess. Other questions or comments on this? It was a good problem, Dawn. This was good.
So in this case, would we just like rely on induction step to check or to like guess Fn or just?
Well, the guess is incorrect, right? So you need to come up with a different guess.
Okay then.
Right? This here doesn't work. So you need to change it. I'm not sure, Dawn. Can you follow?
Yeah, I understand. I just don't know what would be an appropriate guess in that one.
Oh, but I mean, yeah, okay. So this is easier said than done, right? These models that you see presented, it always works out, right?
Okay.
But when you do this, when you start changing things around, it may or may not work out.
Okay.
And so here, I don't think this is going to have such a simple formula.
Okay.
My guess. So here, this is my guess. I think you're going to have a lot more terms. I think you're going to have that Fn is going to be an infinite sum from, but I don't know. This has to be checked. I think it's going to be A. So you have something like A M N. Then I think you're going to have Rn to the power M.
Okay.
You're going to have all sorts of powers here.
All right.
Because every time you include a power, you also need to include the power squared. So the only way I know how to do that is to have infinitely many powers.
Okay.
And this formula here, this is useless because you have infinitely many terms. So I don't. This is this is not a good model. It's not tractable. It's I don't think there is a nice way to write this. Yeah. Are there other questions or comments? If not, then let's try another problem. This was number 8. I had number 14 in mind too. Let's do number 14. So 14 is about comparing futures and forward prices. We talked about that a little bit last time. Here's another specific model that asks you to see if you can compare them. So this is number 14. About that one. So last time we discussed when futures were equal to forwards, and we saw so the futures price, this would be phi n, this one here would be kn, and we saw, well, the futures price, this was given as the conditional expectation of like the terminal value of Fn, and the forwards, this was similarly computable, but here you had to change the measure to a p tilde n, the forward measure of Sn given Fn. Right, so this quantity here, this was a forward measure. And so an easy condition here is, so if Rn is non-random, then the risk neutral measure is exactly the same thing as the forward measure. So this is non-random, we'll have this, and that's going to imply that phi n is equal to kn. So we had quite a discussion about forward measures last time. So here's a so in this problem, you're having in this problem you're given that the expectation under the risk neutral measure of 1 over the money market account, that this is strictly bigger than the expectation of Sn0. Right, so this is strict inequality in Jensen. Inequality. I can't spell inequality. Inequality. There you go. So you can see here, right, Jensen says if you take a convex function, so here the convex function is 1 over x. Jensen says that when the function is inside, you're bigger than or equal to when it's outside. And so here you're going to get strict inequality. So this here, this here implies that Rn is random. Right, because there will be no randomness, then the money market account there would be no need to take an expectation here, and you would have equality. So you have a model here that falls outside of the discussion we had last time. So we cannot say that these measures are the same. Okay, so that's one property that you're given. So you're given this. The other property that you're given to answer this question is Sn0 is given to be independent of Sn divided by Sn0. So you're given these two properties. And of course, in general, this is not the case. You're given that Sn is traded. So now we want to see if we can figure out what the relationship is between forwards and futures. Okay. So what did we have? Very early on today's lecture, we had a discussion about the forward price, and in particular, we've had a discussion about the forward price when the underlying is traded. When the underlying is traded, the forward price simply just becomes the current value of the traded security divided by the zero coupon bond. So let me copy paste that formula. We have here, so for the forward, we will have K0. K0 is this mesh we have in here. This is divided by B0 N E tilde little n is 0. So we're just going to get the expectation. And if you want, we can write this here out. This is a martingale. So this is just going to be S0 divided by B0 N. This was the forward. So that's one expression. Then we also have the futures. And the futures, that was my phi 0. In this exercise, it's called phi 0. I think we called it F before. So for the futures price, this would just be the expectation of Sn. And the question is, what is the relationship? What is the relationship between these two? And so this is where we need to use the assumptions. Like we were given two properties that are not true in general. We were given this inequality and we were given this independence property. So we try to bring them into play. And one way to bring them into play is by working out, rewriting what you have here. For example, I can write this here as Sn0 times Sn divided by Sn0. And then I can use here that these guys are independent by assumption. Right? This is far from always the case, but in this particular problem, it's assumed that these guys are independent. Okay, so then I can break them up. I can now write this as an expectation of Sn0 times an expectation of the other one. Again, the latter part here, this is what I recognize as being up here. This part here, this becomes K0 times B0N. So now can I say something about this relationship? Well, saying something about how K0 in here relates to phi 0, it has to do with how this term relates to that term. Okay, so this is where the other assumption is going to come in. Here we have an inequality. And what I have here, this here is my B0N. The zero coupon bond price at time 0 for expiry at time capital N. Right, so we have that. You have that this quantity, this one here, this was the expectation, 1 over Sn0, right? And this was assumed to be strictly bigger than 1 over, and then the expectation of Sn0. And so if I plug that in, I'm going to get a strict inequality. I'm going to get something that is strictly less than. And so I have this term and I have that term. They will cancel out. I'm just left here with K0. So in this model, when you have those two assumptions, you have stochastic interest rates, and you have this independence property. Under these two conditions, you will see that the futures price strictly dominates the forward price. Are there any questions or comments on this part? So again, these two properties here, the special, this is something that is only true in this problem. It's not something that is true in general. Whereas what we had discussed up here, like that the futures price is a conditional expectation under the risk neutral measure, and the forward price is a risk neutral expectation under the forward measure. These properties, they hold true in general. These two properties here that we used to get the relationship between forwards and futures, this is something that is more special. Are there any questions about these two things? We good? Dawn is good. So keep in mind, there is no way for me to read your minds, right? So if there's something that is not clear, I can go slow, but I cannot. I can't see what's on the inside of you guys. So you got to speak up, right? If there's something that is not clear. Alrighty. So before we take a little break, let me just outline what we're going to be doing after the break, right? So after the break, we're going to look at more popular. We're going to look at more popular fixed income. So next, we're going to be looking at more fixed income derivatives. So a very large class of assets is interest rate swaps. These swaps, they're very important for they're very important for calibration. They're quite important for that. We're going to be looking at those, and then whenever you have, this is again one of these linear contracts, so it's going to be very similar to forwards and futures. We're going to be looking at options on swaps, and these are called swaptions. So we're going to be spending some time doing these after the break. Then depending on how much more time we'll have, we can also move on to looking at floors, caps. So these are options on R, the interest rate. And we can also look at options on zero coupon bonds. And I think this is going to be it for today. Okay, so this is one I'm going to come after the break. Now let's take a little break, switch over on the other Zoom link, and then in 10-15 minutes, let's start back up. Okay, I'll see you guys soon.
All right, thank you, Professor.